Now let's look at the inverse tangent function. So the inverse tangent function is, as you can see, 1 to 1 on the interval from negative pi over 2 to positive pi over 2. So in this case, we'll restrict the function tan of x to the interval from negative pi over 2 to positive pi over 2. And so we'll say that y is equal to tan inverse of x if and only if x is equal to tan of y, where y is strictly between negative pi over 2 and positive pi over 2. And notice that we can't include those endpoints because we have vertical asymptotes in the graph of tangent there. So tan of pi over 2 or tan of negative pi over 2 is undefined. So let's look at an example here where we're simplifying an algebraic expression of the form cosine of tangent inverse of x. So similar to how we did this before, I'm going to start with saying theta equals to tan inverse of x. And then I can say that tan of theta equals x over 1. So doing a little right triangle trigonometry with the angle theta here, we know x over 1 would be the opposite over adjacent sides, since the tan ratio is the opposite over adjacent side. So with a little right triangle trigonometry, we can, with a little Pythagorean theorem, we can solve for this missing side as the square root of x squared plus 1. So to get cosine of tan inverse of theta, well, we can think now the cosine of theta, right? Since we've replaced this tan inverse of x with a theta, will be the adjacent side over the hypotenuse. Because, right, we know that for cosine it's the adjacent over the hypotenuse. So here we have an algebraic expression for this function cosine of tangent inverse of x. Let's look at the graph of tangent inverse. Now the nice thing about the tangent inverse graph is it tells us a lot about the function itself. For instance, we notice that the domain of tangent inverse is all real numbers because it can go to the right or to the left forever. But the range is always going to be between negative pi over 2 and positive pi over 2. And we also notice that as x goes to infinity, the graph will tend towards positive pi over 2 as it goes to the right. And as x goes to negative infinity, it'll tend towards negative pi over 2 as it goes to the left. So with this picture in mind, we can oftentimes remember those two limits very easily. How about this limit as x approaches 2 from the right of arctan of 1 over x minus 2? Well, what I notice is that 1 over x minus 2, 1 over x minus 2, as x approaches 2 from the right, well, we're going to get something that approaches 0 in the denominator. So when I get something that is 1 in the numerator but approaches 0 in the denominator, we get something that's going to blow up. In other words, the value here is going to go to infinity or to negative infinity. So what is it in this case? Well, since it's approaching 2 from the right, we're approaching from values of x that are greater than 2. So therefore, x minus 2 will always be a positive value. So we can imagine that this is going to be going to 1 over 0, where 0, it's approaching 0 from the positive side. So this is actually going to approach infinity as x approaches 2 from the right. So this would be the same as saying the limit as t approaches infinity of arctan of t, right? Because here I'm just sort of substituting in the value. T equals 1 over x minus 2, where we see, yeah, t goes to infinity as x goes to 2 from the right. So we can write the limit as t approaches infinity, arctan of t will be, well, if we remember, we saw in the previous slide that the graph of arctan will tend towards pi over 2 as it goes to the right. Here, let's consider the derivative of tangent inverse of x. So we've done a similar derivation with the other ones, where if I say y equals tan inverse of x, we can do it implicitly by writing x equals tan of y. And in this case, the derivative applied to both sides of this equation gives me 1 equals the derivative of tangent, which is secant squared, times y prime. And hence I get y prime equals 1 over secant squared y. Now before we can get the answer here, let's think about the way that secant squared relates to tangent. And we have this important trig identity, 1 plus tan squared equals secant squared. So in fact here we can write 1 over secant squared as 1 over 1 plus tan squared. And then tangent is equal to x, so this is the same as 1 over x squared. Sorry, 1 over 1 plus x squared. So there we have the formula for the derivative of tangent inverse.